So I left you with this example. Plot it out this particular sinusoid function in the time domain. So if we do that, what we'll see is that we have a sine wave that is shifted. We can tell the shift because of this minus pi by 2. We could convert it to a cosine if we like, in which case to move between a sine and a cosine, we simply take away pi by 2 from this phase element. So minus pi by 2 minus pi by 2 would give us minus pi. So either way, you can see that a sine function would normally start here. To get this negative phase shift, we move the axis backwards against the signal, or the signal forward against the axis. So we actually start down here at minus 1. Well, that would be for a sine, but we have this amplitude here. So we can now say that our amplitude is going to vary between plus 4 at the maximum here and minus 4 down at the minimum here. We can also show that we need to know about our number of cycles. So we have 40 pi as our frequency in hertz. So this is 40 pi as omega, our angular frequency. Well, we know that to convert between the two, we've got omega is 2 pi f. So in which case f is just going to be omega on 2 pi. So our f is going to be 20 hertz. So that means we're going to have 20 cycles of this in any second, which means that each cycle is going to take up a period of 1/20th of a second. So we've got the initial phase, we've got our maximum and minimum amplitude, which we take from that element, and this element is going to give us the time that it takes for a cycle. So those should fill in here correctly. So we can describe any of our sine waves by just 3 elements: amplitude, frequency, and phase. The height, how fast it changes, and where it starts against t equals 0. And we can plot those against time. But what happens if we want to plot against frequency, and why might we want to do that? Well, we can also use the frequency domain. So here you'll notice that we have f. I should put this in hertz, although you can do it in angular frequency by the same token. And here we're going to draw a line whenever we have a frequency element. So we would draw f0. In here we would define f0 as being 2 pi f0 being omega 0. We have our amplitude, so we've got this element and this element, but we also need a phase element. So whenever we draw in the frequency domain, we need to have 2 graphs side by side. One that shows the amplitude spectrum at the top, which is amplitude versus frequency, and a phase spectrum, which shows phase against frequency. I don't actually know what this phi 0 element is, so I'm just going to draw it somewhere between minus pi and plus pi, because we said we never go beyond that scale. So why might this be useful to us? Well, imagine we had 2 sinusoids and we added them together. It would be quite difficult to work out actually what the time sequence is actually going to be when we add those 2 together. You'd actually have to go t by t, draw dots, and actually plot it through. So if we add these, the equation looks quite simple, but actually the time domain spectrum is quite complicated. What we actually have here is, you can sort of see a sine wave like that, and you have another sine wave inside. So you have one sine wave modulated by another. It's actually quite difficult to see how that time sequence comes about from this equation. Equally, if you were given this, saw this as a time sequence, to work out what the sinusoids that make it by adding together, it would be quite difficult just by looking at it to work out that there are these 2 adding together. And that's when there's only 2. So if there's many more sinusoids adding together, it gets increasingly complicated, which is why we use the frequency domain. In a frequency domain representation like that, we can quite easily see the sinusoid or cosinusoid components that add together to make up a spectrum. So if we take this equation that we've got here and plot it, we will have one element at 50 hertz. I should put hertz on here. One element at 75 hertz. And we also need phase. The element at 50 has no amplitude value. The element at 75 has an amplitude of 2, and we can draw that on the graph here. And we can draw 0 phase change and a minus pi by 2 phase shift for the two elements here. So this spectrum shows us all the frequency components that make up our signal. So with that in mind, I'm going to give you another little exercise to follow. Here we have a cosine function, and we also have a sine function. Now if you remember here, we didn't actually discriminate between what was cosine and sine. Both of ours here were cosines. And we'll use the convention that we always plot, and it's most relevant for the phase spectrum, we always plot against the cosine. So you have to make sure that you actually plot this correctly.